Welcome everybody to the last video of this course. It's going to be kind of a nice departure from doing integrals the entire time as we kind of return back to a little bit of calculus 3 and focus really much on partial derivatives, much more than we're going to be focusing on integration. Actually, we're not going to be doing any integrating at all, so this topic is kind of left for the end of the course because I feel like it's a little strange to do it at the beginning, kind of gets left out, and then, if we do it in the middle, it kind of interrupts all of the integration that we've been doing and all these line integrals, surface integrals, things like that. So here we are, and we're talking about optimization of 3D functions. And if you remember all the way back in Calculus 1, optimizing usually had to do with derivatives because we were looking at a function and we were wondering, when does that function achieve a maximum, right? Optimizing something, usually we wanted it to achieve a maximum or a minimum value, and the optimal values of a function usually happen when f prime of x is equal to 0. That's when max has occurred, or that's when maybe we wanted to use the minimum amount of fencing to build something, or we wanted to make the most amount of something. We wanted to first figure out where the derivative was equal to 0, and then we kind of had to check, right? We had to make sure that this was indeed a max or a min, because if the derivative equals 0, we could have 2 or 3 cases. We could either have a max, we could have a minimum, or we could, have nothing, right? And the example for the nothing case was if our function was kind of flat like this, if you test the derivative right here, you're going to get that the derivative is equal to 0, right? The graph is technically flat at that point. But what we would do is you could do a concavity test before and after, right? A second derivative test to kind of clearly see that, we're going from concave down on one side to concave up on one side, and that's kind of a problem because if we had a maximum, we would just be concave down on both sides. Or you could do the first derivative test, and you could just simply see that the slope of our graph, right, f prime is positive here, and then the slope of our graph on the other side is also positive. But clearly, if we had a maximum, then the first derivative should go from being positive down to being negative, and vice versa if we had a minimum. So this is kind of just a brief review of optimization, of finding maxes and mins from Calculus 1. And the word optimization usually just came from us trying to find maximums or minimum values. Like I believe the standard examples are taught, or like the minimum amount of fencing required, or the minimum amount of water, or the minimum distance of something, right? It's usually maximizing profit or minimizing something happening. And so while that's very easy to think about in 2D, where we have like maxes and mins, it is a little bit, not just a little bit, it's quite a bit trickier to think about talking about maxes and minimums of a 3D function. Because a 3D function comes with 2 variables, and you could have something that looks like this, right? And this could be, kind of maybe parabolic in shape. So maybe there's like these, it's round, at all these different places. And you're trying to determine where there's little local maximums, where there's little local minimums, things like that. How do you do this? Okay, because there's not just one direction to talk about. We don't just have an x and a y. We have an x, a y, and a z. Okay, so the goal with this section is to figure out how to find, the max or min of a 3D function. Okay. Now, I'm just going to kind of break us straight into the intuition, the way I like to think about it. And it kind of should make sense, right? So let's consider just a simple shape like a regular paraboloid. Okay, so just something that's nice like this. Okay, clearly has a minimum. All right, clearly has a minimum. Now, the question is, at this minimum, we want to know what is true. Okay, what is true? at a minimum or maximum. Okay, what is going to end up being true? And it turns out that, we are kind of interested in the same things that we are in Calculus 1. It should make sense that if I'm at the minimum, then if I were to figure out the derivative with respect to x, right? If I were to take the partial derivative with respect to x, then this thing should probably be equal to 0 because I have to be at the bottom, right? If I were to take that yellow point over here and take the derivative with respect to x, right, the graph is going to be sloped down, it's going to be negative. And if we're at the bottom of something, we want to be nice and flat, so that should mean that our f prime with respect to x, our df dx, right, df dx, should be equal to 0. Now, likewise, it should also then make sense that if we are doing the derivative with respect to y, because that's our second variable, right, we also need this derivative to equal 0, right, the partial of our function with respect to y, because if we're at a minimum, right, it is entirely possible to be up at this yellow point up here and to talk about the slope in the x direction could still be 0 here, right? We could still have the slope being 0, but if we talk about the slope going in the y direction, right, clearly we're tilted down, so we're not at a maximum or minimum. Okay, we need both of them to be flat, and the same thing goes with the maximum. So one standard that we have, our very first thing to find critical points have to be located. They have to be located when both the partial derivative with respect to x and the partial derivative with respect to y both equal 0. That's the first check that we have. Now, just like with our 2D case, right? We have 3 cases that could happen. We could get a maximum, we could get a minimum, and we could get nothing. And now that we're all a little bit older and a little more mathematically mature, this point right here, this kind of nothing case, is what we call a saddle point. Okay, we call this a saddle point. And the idea is that we've achieved flatness for a second, but in reality it's still not a max or min. And so what does this look like for a 3D function? I'm going to do my darndest to try and draw it. But we've clearly seen, where we might have a minimum, and we've kind of seen, you can imagine just the same idea upside down for a maximum, right? Those are the easiest ones to comprehend, but it's totally possible for us to have a shape that looks kind of like this, maybe. I'm gonna do my darndest to draw this correctly. I don't know, something like this, okay? It's entirely possible to have some function, right, a hyperboloid or something. And the problem is that if I go to this point right there, the derivative in the x direction is equal to 0. The derivative in the x direction is 0. And the derivative in the y direction is also 0 at that point, right? It's flat at that point. But clearly we can see that it's not a minimum, right? And how do we know that, right? Let's zoom in a little bit. Let's think about it. If I go over here, right? If I kind of go down this trumpet looking shape right here, clearly I've gone lower, right? I've gone lower in at least one of the directions, in the z value direction, right? My f value is clearly lower, right? Now, if I were to go for a walk in this direction, yes, all of these points over here are higher, so it seems like this point that we've picked is a minimum, but in fact, it's kind of like a false positive because we can see that I can clearly go for a walk down here and achieve even lower points. And so this is what we call a saddle point because it looks like a saddle in the graph. And it's very analogous to the situation that we used to have, specifically when we used to have the graph y is equal to x cubed, where when you took the derivative of this, we'd get y prime is equal to 3x squared. And so we'd say, oh, there's a critical point when x equals 0, but we clearly can see from the graph, and we can use the first derivative test or a concavity test or whatever you like to clearly see that this is not going to be a maximum or a minimum. So the very natural question is, since we're in 3D, how do we verify, right? Once we have satisfied this, right? Once we have our critical points, how do we make sure that we have a maximum or a minimum? Okay, and so, well, I'll go ahead and just kind of write it down. So here's the idea. There's a test that we run to make sure. So this is like part 2. There's a test. And the test is that we're going to solve this thing right here. And I'm going to explain exactly what this is. So here's the test. It's f sub xy squared. And these are all at whatever point that we're on. And usually they say that this is equal to the letter d. They just give it a letter d. But the equals d doesn't matter. The test is as follows, right? So let's think about what could happen in this test, okay? You'll notice that when it comes to looking at this horn-shaped looking thing, okay? Actually here, let's go back up to the paraboloid all the way up here. In order to have a chance of being a minimum, we have to be experiencing concave up in the y direction, and we have to be experiencing concave up in the x direction. We have to be experiencing this. If not, this is clearly not going to be a minimum, okay? So here we have, in this situation for a minimum, we have that both of these are concave up, okay? Now, for a maximum, it's going to be very similar but opposite, right? We have to make sure that in the x direction, we're concave down, and in the y direction, we are also concave down. So in order to get a maximum, we would need this to happen, right? Okay. So the idea is that no matter what, okay? So I'll write this down. No matter what, we need the partials, the second derivatives, to match, to even have a chance. To even have a chance to be a max or a min, right? Both have to be concave up, or both have to be concave down to be a max or min, okay? If you look at this shape right here, you'll notice that we are concave up in the y direction, but in the x direction, we are very much so concave down as we kind of come the other way. And so you'll notice when these don't match, right? When one of them's positive and one of them's negative, last time I checked, a positive and negative multiply to give me a negative, this thing is going to evaluate to a negative. And if I take a negative number and I subtract something that is always positive, right, because we're squaring this, if I subtract something that's always positive, this value, this number that we're going to get out of here, is going to be negative. And so the first result of this test is that if this value, if d, if this thing that we're evaluating is negative, okay, this means that we have a saddle point, no max, no min. Okay, that one should make the absolute most sense. Okay, so we have to find a critical point first, then we try and figure out, is it a max, a min, or a saddle point? If this value ends up being negative, or if the concavity doesn't even match, if these two do not match, we are going to get a saddle point 100% of the time. Now, what happens when they do match, right? What happens when these two are the same? Now, that gives us the other case. So if this is positive, okay, if this is positive, right? And the second derivative, right? If we're concave up in the x direction, well, if we're concave up, right, if we look like this, that means that we should have a minimum, right? So then we have a minimum. And the other case is if d is positive and we are concave down, then we have a maximum. And that's it. That's all there is to it. Now, people ask, does this have to be f sub x, or the second derivative with respect to x? No, because remember, in order to have a max or min, both the partial derivative with respect to y and the partial derivatives with respect to x, they both have to match. So you could have used the fact that, you know, we're concave up in the x direction, or you could have used the fact we're concave up in the y direction to figure out that we had a minimum there. Okay, so this is in the textbook. It is on page 961. This little formula right here, and I'm just going to go ahead and do one example that kind of shows how we use this, you know, in an actual problem. So this is an example from the book, but it says, you know, find the local max and min, or saddle points of the function, of the 3D function x to the fourth plus y to the fourth minus 4xy plus 1. Now, I have no idea what this function looks like, and to be honest, I don't really care. Maybe it represents the amount of money that we're making based on cookie sales and what day it is, right? I have no idea, don't really care. That's not what we're in charge of. We're not in charge of caring. Our job is to basically just evaluate maxes, mins, or saddle points. So the very first thing that we're going to do is we need to figure out what is the partial, like we need to figure out when does this equal 0. Okay, so in order to do that, we first need to figure out the partial with respect to x. So we get 4x cubed minus 4y, and we need this to equal 0. On the other hand, we also need the partial with respect to y, the first derivative, to equal 0. And so that is going to give us 4y cubed minus 4x is equal to 0. And I need both of these to be true at the same time. Otherwise, we have no critical points. And so that means I need both of these equations to be true. So let's go ahead and solve them. And I'm going to take this first one and I'm going to rearrange it simply to just be x cubed is equal to y. If I add the 4y to this side and then divide by 4, I get that equation. And I'm going to plug it in over here for y, because again, I need both of these to be the same. So we're going to get 4 times x cubed minus 4x is equal to 0. And let's see, where does this take us? So this gives us 4x to the 9th minus 4x is equal to 0. And that, we can cancel out a 4 and an x from both sides. So we just have x to the 8th minus 1 is equal to 0. Now, the book at this point uses some fancy algebra, and I will too. So we need to remember what a difference of squares basically becomes. And I guess at this point, I guess I forgot to write that not canceling the x because x equals 0 is an opportunity. We're just going to factor out the x. Okay, and so to get to here. And so what we're going to have is we're going to have x times, now x to the 8th minus 1 is a difference of squares. So we can write this as x to the 4th plus 1 times x to the 4th minus 1. And then x to the 4th minus 1 is also a difference of squares. So that's x times x to the 4th plus 1 times x squared minus 1 times x squared plus 1. And x squared minus 1 is also a difference of squares. So we get x times x to the 4th plus 1 times x plus 1 times x minus 1 times x squared plus 1 is equal to 0. And again, what are we doing? We're trying to find our critical points right now. And so far, according to this equation, we have the situations when x is equal to 0, when x is equal to -1, and when x is equal to 1 are going to be our possible critical points. Now, because this is a 3D function, we also need y values, and so we can figure out the associated y values by plugging in to f of x sub y. Actually, can we do this? No, we don't do this. We're not plugging into f of x sub y. We're going to plug it into our f sub x. Or f sub y, it doesn't really matter. But you can plug them in to either one of these and figure out what our corresponding y values are. So I'm going to choose to plug them into 4x cubed minus 4y equals 0, which we said was simply the equation x cubed is equal to y. And if we do that, if I plug in x equals 0, then we get the point y is equal to 0. If I plug in x is -1, I get the point y is -1. And if I plug in x is +1, I'm going to get the value y is equal to +1 as well. So here are our potential critical points. We have 0, 0, -1, -1, and 1, 1. These are potential maxes, mins, or saddles. Now, in order to determine if they are maxes, mins, or saddles, we do need to figure out and set up our second derivative test. We do need to do our concavity check. And so, using that thing I circled at the top, circled in yellow, we're going to solve for the second derivative with respect to x. And that, since this was the first derivative with respect to x, the second derivative is just going to be 12x squared. The second derivative with respect to y is going to be 12y squared. And then just for kicks and giggles, we will also do f sub xy squared. And so that's going to be, so we already did the derivative with respect to x. That was the 4x cubed minus 4y that I have circled in green up there. So if we take the derivative of that with respect to y, we're going to get just -4 squared, which is 16. So setting up our little test that I kind of reasoned to us earlier, right? We're going to use the fact that d is equal to, all right, so it's f sub double x, so it's the second derivative, so that's 12x squared times 12y squared minus 16. All right, and so that simplifies to 144 x squared y squared minus 16. That's our d value. Now, what are we doing with this? Again, right, we are simply going to test our critical points in here and make sure that we have, right, where did this formula come from? It came from the explanation I gave earlier, where the matching concavities, all that good stuff. So we're going to do this test, and we're just going to do it for all 3 points. So what is the value of d at the point 0, 0? Well, that's just going to be -16, which last time I checked is a negative number. Right? It's negative. It's a negative number, and when d is a negative number, as we kind of see up here, we get a saddle point. So this is a saddle. This is a saddle point. Now let's do d of -1, -1. So that's going to give us a positive 144 minus 16, which is 128, which is definitely greater than 0. So we either have a max or a min here, right? We either have a max or min. And the way we test that is it concave up or concave down? So let's just go to our second derivative over here, and let's plug in the point -1, -1. And we clearly see that we're going to get that the second derivative evaluated at the point -1, -1 is going to be a positive number, right? It's going to equal 12 times -1 squared, which is just 12. So this means that the second derivative is positive. We're concave up, which means we have a minimum. So we have a minimum at this point. All right, cool. And then last but not least, we're going to evaluate the value of d at our last interesting point, our last critical point, which is going to have the exact same value of 128. which is positive. So again, we either have a max or min. So we need to test it. Let's plug it into the second derivative of x again. We're going to get the exact same answer. So this here is also a minimum. And you might be wondering, well, how could all of those be minimums? Well, maybe our graph or maybe our function has a part where we experience a minimum, and then we experience a flat, and then we experience another minimum, and then we go up like this, right? So maybe this is going to be our graph. So we experience a minimum, we experience a saddle, we experience another minimum, and we just end up kind of going up the rest of the time. Okay, so that's going to do it for basically optimization. Now there is a little bit more to this. There is a little bit more in terms of absolute maxes and mins, and you can read about it in the text. But I will not test you on that. It's fine. It's not super important to what we've been doing, but that's going to do it for this video. Hopefully you enjoyed this last kind of interesting way of figuring out how to maximize and minimize when we have multiple variables in our functions. I hope to see you in whatever math class you end up taking next.